Welcome everyone. So today, Stefano Fiovaranti, currently in Charles University Prague, will talk on some admissible sublattices of a congruence lattice. Please.
So thank you, Peter, for the introduction. So what this talk is about? Of course, there are a lot of classical results about congruence varieties and how to classify and to characterize especially admissible condition through the omission of some lattice in the congruence variety of a variety. And this talk, of course, is following the path and is mainly about also what we called, and by we, I mean me and my co-authors, so Paolo Agliano and Stefano Bartali, that we called Freeze technique, that is dedicated to Ralph Freeze, since it was it was a technique to build congruence lattices from basically another congruence lattice, passing through, let's say, a new algebra, so changing the algebra that you consider, of course, building this algebra using as a base set a congruence of the original algebra. And so, of course, some of the informations are passing through the first lattice, so the congruence lattice of the original algebra to the second algebra, and you can say something. So that's the main argument of the talk. I think so. The first idea comes from a paper of Freeze, but I guess it was also used in the proof of the Desargues law for projective planes, I guess. So this is the how the idea was developed through the year to actually starting from classical results. So let's go further. So a little bit of notation and definition, just to start. Of course, we will consider algebras and we will consider congruences of an algebra. And in particular, we need the concept of relational product, and in general of k-fold relational product. That is the relation in general defined in this plane. So we take the set of pairs such that there is a chain of elements in the algebra connected with the application of k application of the congruences involved in the product, of course, where first you have to apply alpha, then beta, and so on. And of course, C0, the start of the chain, is the first element that you have in the pair, and CK is the second. We will denote, as usual, the two relational product with the circle without the exponent. And of course, we can see that, as usual, we can consider the join of two congruences of a congruence lattice as the union of all k relational products. And I have also to introduce modularity and distributivity for lattices, because yeah, the talk is mainly concerned about those class of lattices. So this is one of the possible, of course, presentation of modular lattices through the quasi-equation display. So a lattice is modular whenever taking A, B, and C with C less or equal A, then you have A meet B join C less or equal A meet B join C. Distributivity, of course, I will not display the distributivity between join and meet. That are mainly the two laws obtained when join and meet distribute with respect to each other. And the two classical examples that actually we use, so let's also introduce and recall them, of non-modular lattice with 5 elements, the one in the left, and modular lattice with 3 atoms, the one in the right. And that's probably that's the reason also for the symbol N5 and N3. Of course, why it's important, or was or important to consider inclusion and exclusions of certain subpattern, in this case sublattices of lattices in general, and how they characterize properties. So this was, I guess, firstly discovered by Dedekind and Birkhoff with the two classical results that describe modular lattices and distributive lattices as the one that exclude the first N5 and the second N3 and N5, respectively. So an example, D2 is not modular because it has a sublattice that is isomorphic to N5. So that's all about, I guess, the general introduction and what we need about classical results, I guess. And so what will be our strategy to say something about properties, something about, in this case, exclusions or inclusion of some sublattice in the congruence lattice of a variety. We will do that using the strategy developed by Fries that I mentioned at the beginning, that is to consider some congruence. In this case, it's more complicated in general definition, but basically what we will do is to consider some congruence of an algebra as the algebra that we want to study congruence-wise, so a congruence lattice-wise. So we want to see what's the congruence lattice of a congruence given the congruence lattice of the original algebra. To do so, we introduce the algebra that we are talking about. In the general case, it will be this A up to the n alpha, where alpha is a congruence and A is the original algebra. And we take as a base set of our algebra the set of all n tuples in the power of the original algebra, such that every pairs that you can form in the tuples is in the original congruence. And so the first question, the question that we want to investigate is for a given lattice and a given variety in general. Let's take A in the variety. When we can build such a power of the algebra such that L is a sublattice of the congruence lattice of, let's call it, of this synthetic algebra. So the algebra that we built in the variety using a given congruence of the original algebra. So this is what we wanted to investigate. We, in general, we fixed for almost all the cases, since it's already quite complicated, n equal to 2. That was also the case studied by freezing some settings also, and some other also researcher. Also in our result, we used also some higher power to form some chains of lattices that we want to admit. So in almost all the cases, the n will be fixed to 2, but in some cases not. And also we will define what are the admissible lattices of a variety. They are simply the set of all lattices that are sublattices of some congruence lattice of an algebra in the variety. So why the strategy that we will introduce was useful, especially in some classical results, but also I would say, some recent results. So I have included some results in the literature that were more or less proven using the technique that I mentioned. Some of them can be of course also provable without it, but so here I will use the notation of MP for the congruence variety of the vector space over a field of characteristic P. And so a result in the literature that was proven also by Fries in a paper of 95 is that there are no modular varieties of lattices that are not a congruence variety. So they are generated by the congruence lattice of a variety. And so this is actually, there are many results, I would say, proving this fact, so that there is this that not all varieties of lattices are congruence varieties. I will show also an example of it as a toy example also for the technique that we will use. Another result, still by Friel and also Bernie Johnson, every modular congruence variety consisted of entirely Argesian lattices. And there are also many others. For example, these three. So every non-modular congruence variety contains conp P, where P is the polyvariety. Every modular non-distributive congruence variety B contains MP for some P, and also the recent result, if B is a variety with a weak difference term that is not congruence Smith semi-distributive, then the congruence variety of B contains MP for some P. So just to start with the example that I will show, that it was in the paper of I guess the 95 of Fries. Let's also introduce the notation that I will use about the congruence series of A alpha. So the algebra or the subalgebra of the direct product a to the square, given considering as a base set alpha. I will use this theta zero notation for the factor congruences, the factor congruence A0, A1, B0, B1, when A0, B0 is in the original congruence theta of A. Same with theta 1, the second component. And also I will use the eta 0, eta 1 notation for the kernels of the projection over the two factors of A alpha. And of course, by the homomorphism theorem, we will get that we get in the general case that the congruence lattice of A alpha factored by one of the two kernels is isomorphic to the congruence lattice of A. So also some basic thing that you can prove considering gamma and theta in con A are the following. So if you consider the congruence lattice of A of gamma, whenever you choose a theta that is over gamma, then the theta 1 and theta 0, the factor congruences are collapsing in one congruence. And this is actually where you attach the two copies of the original congruence lattice that you obtain in the congruence lattice of A of gamma, given by the homomorphism theorem. Also, another thing is that is easy to prove is that theta I is equal to eta I, the kernel join theta 0 meet theta 1, and the gamma 0 is equal to the join of the two kernels. So you obtain the factor congruence correspond to the original congruence gamma that you start to build the algebra, doing the join of the two kernels. So to give a real example, so an example of an application of how we can characterize the congruence lattice of A of gamma in this case, no, A of beta in this case. Okay. Let us apply, so let's consider this pentagon labeled as in this way, and let us apply the technique let us consider A of gamma in this case. So in a result of freeze, it was proven that A of gamma is uniquely determined for every pentagon, and is this lattice L14. So the name actually comes from the result of, I guess, Johnson Rival, that is characterizing the covering of all the coverings of the smallest non-modular congruence variety, that is the variety generated by N5. This is one of the lattices. They are 16, and so yeah, that's why L14. So, and now you actually obtain this lattice as the lattice of congruences of A of gamma. So first you start from the top. Of course, you have the two copies given by the homomorphism theorem. Both are over the two kernels, of course. They are attached over the edges that are over gamma 0, since of the previous lemma. And so from the previous lemma, we know that every congruence that is greater or equal than gamma produce factor congruences that collapse. So the 0 and the 1 are the same. Then, of course, you have to prove that the other joints emit are correct. So first of all, you can prove, for example, that if you do the meet between the beta 0 and beta 1 and the ethas, you obtain the bottom. So that is the meet of the two kernels. You can still get this by the lemma that I showed you before. About the join, for example, you could check that the join of the eta 0 and beta 0 meet beta 1 is respectively, if you do the join with beta 0, you obtain beta 0. If you do the join with beta 1, you obtain beta 1. Still, you can get this from the previous lemma. And actually, no other join is relevant to characterize, because the others are following either from the homomorphism theorem from so for the edges, so for the upper parts, and for the bottom, yes, they are all the interesting ones. So okay, so that's a first application. Actually, this is already proving that not all the variety of lattices are congruence variety, because as I stated before, this is one of the covering of the minimal of the smallest non-modular congruence variety, that is the variety generated by N5, and we have basically proved that the variety generated by the congruence variety generated by N5 includes L14, that for standard lattices is a strict covering of the variety generated by N5. So we have already proved that actually the variety generated by N5 is not a congruence variety. So another application that this is the application that we first tried for this technique, was to still consider N5 labeled as before. So just to re-see it with the beta, that this is the standing alone congruence in the left. So what about cone A of beta? What were the question about it? Is cone A of beta uniquely determinate? The answer is no, and was already observed by Fries. To do that, also let's say something about the situation of the congruences in this context. So first of all, we can observe that simply by by the fact that that the meat is monotone in both components. We can observe that gamma 0 and gamma 1 is contained in all these three congruences because alpha is greater than gamma mainly. Second, these congruences are strictly less than alpha 0 meet alpha 1 in all the cases. And then if the two congruences alpha 0 meet gamma 1 and gamma 0 meet alpha 1 are comparable, then they collapse. They collapse all in gamma 0 meet gamma 1. And that was the main two. That the main actually is not so hard. So the first two things are quite easy to prove. The third one, you have a little bit of computation to do, but it's not hard to do it, to prove it. And not actually what was the second one is the really not trivial one. And this is actually what characterized the two cases that you can obtain considering cone of A of beta. So they are mainly when these two congruences are collapsing in gamma 0 meet gamma 1 and when they are not. So, and in the case they are collapsing, so in the case they are comparable, we discovered that basically you can prove that the sublattice of cone A of beta generated by these congruences, so you take alpha 0, alpha 1, gamma 0, gamma 1, and beta 0, is this lattice M1. How do you prove that? You redo what we have done in the example of L14. So in the two sides, you have still a copy, two copies of N5, attached from the edge that start, so glued from the edge that start in B0 for the from the lemma that we have proven before. Then there should be something else that actually disappear from the slides. No, maybe. Okay, it was the wrong side of the arrows. Okay. So then you, of course, you have to start to prove that the other joints and meet are correctly depicted in the picture. So, for example, mainly the interesting ones are the one between the chain on the left over N0. So you take an element in this chain and you take an element in the other chain in the right, so over N1, and with the chain in the middle. So for example, we know, since we assume that alpha 0 meet gamma 1 and gamma 0 meet alpha 1 and gamma 0 meet gamma 1 are collapsing in gamma 0 meet gamma 1. Using the lemma that we have proved before, we can also prove that what is the joint between gamma 0 and alpha 0 meter alpha 1. And that actually basically all, because all the other joints follows from either from the homomorphism theorem or from the order between the original congruences alpha, beta, and gamma. In the other case, so what's happening? So the other case is when alpha 0 meet gamma 1 join alpha 0 meet alpha 1 is not alpha 0 alpha 1, and the two congruences are not comparable. In this case, it's not hard to prove that the join of the two is strictly less. And you obtain, in this case, this K lattice. So what's happening is actually that, what you get? You get a theta in the middle, that is the join of alpha 0 meet gamma 1 and gamma 0 meet alpha 1. And of course, you obtain, with respect to the M1 that we have seen before, you obtain also the two congruences that are not collapsing. So you obtain this kind of square in the middle that it's collapsing in the case of M1. In order to prove that the join and the meet are correctly depiched, in this case, it's a bit harder. What's the problem? The problem is actually the join between gamma 0 and theta that could potentially generate another factor congruence, let's call it theta 0, not theta 0 because we already used, maybe we use gamma, phi 0 between gamma 0 and alpha 0 in general. To exclude actually this case, of course, we can suppose that in cone A, the interval between gamma and alpha is actually composed by only two congruents, gamma and alpha. So we have anything in the middle. And this actually exclude the congruence that you could potentially generate between gamma 0 and alpha 0. That was the way how we actually exclude this case. And this is not actually a so restrictive hypothesis. We will see why. And so in this case, when you restrict the N5, when you say that the N5 in cone A as the interval gamma alpha that is actually composed by only two congruents, then you have this dichotomy that we have seen before. So the sublattice L of the congruence lattice of A of beta generated by alpha 0, alpha 1, gamma 0, gamma 1, and beta 0, so the congruence that we studied before, is either K when alpha 0 meet gamma 1 and gamma 0 meet alpha 1 are not comparable, or M1 when they are. And so that's the characterization. Of course, this result can a little bit strengthen because since we are talking about the congruence lattice, and since congruence lattices are weakly atomic, if we have a copy of N5, a general copy such that we don't have the interval gamma alpha that is actually composed by only two congruences, we can actually find as a sublattice of this N5 an N5 satisfying the hypothesis of the theorem before. And so we can actually conclude that if you have an M5 as a sublattice of your congruence lattice, and you take a sublattice of M5 that is another copy of M5, where the interval alpha gamma is composed by only two congruents, and you can always do it, as I said before, then you find that actually the dichotomy holds in general that we have shown. Either you produce a K or either you produce an N1. Furthermore, we also characterize when you produce K or N1 in terms of the properties of the original congruences and how they are related to the three-fold relational product. In particular, you obtain a K if B circle gamma circle beta meet alpha is not contained in gamma, and you obtain M1 otherwise. So actually, given the congruence lattice and given the three congruences that you are interested in, I can tell you from the congruence when you are in an easy way when you are generating a K or an M1. Indeed, one of the first questions I guess one could ask is are there actually algebras that are showing that all the two cases are plausible? So are there any algebras, any real example of algebras with a congruence lattice of A of gamma or A of beta, let's say, that is really K or M1? The answer is yes, but I will show you in these other slides. Yeah, maybe before the example, then I will return to this corollary. The answer is yes. So, for example, for M1, how do you build that? So the strategy is to consider a set, possibly with the fewest amount of elements, to construct a partition of the set. So to consider the algebra with only projection as operation, and was base set is the selected set, to construct a partition that it generates an M5 like this one, and satisfy one of the 2 points of the theorem before. In this example, alpha, beta, and gamma generates an M5 inside con A, and in this case, they satisfy point 2. So beta circle gamma circle beta meet alpha is contained in gamma, and you can check it. So the only pair that is not the only pair that is not collapsing in gamma is 1, 6. And if you consider beta circle gamma circle beta circle gamma, no, beta circle gamma circle beta circle beta, you get what you want in a smart way. The other case, of course, when you don't get this, you can still obtain with the same strategy. Considering, for example, this example, you have 1, 2, 3, 4. You have beta, you have beta, gamma, and alpha given by this partition, and in this case, you generate K as the congruence lattice. And if I can, let's go back to the corollary. Yes. So furthermore, if we add some hypotheses about the original variety, so for example, saying that the variety is satisfying a non-trivial idempotent Maxwell condition, then we can actually say that the only possibility left is that K is the sublattice of the congruence lattice of A of beta produced with the procedure that I explained before. This because M1 is excluded, since satisfying a non-trivial idempotent Maxwell condition implies that we have to exclude D1 as a congruence lattice, as a sublattice of our congruence lattice. And in this case, the filter given by gamma 0 beta gamma 1 is actually a copy of D1. So yes. So that was our first real application of the technique. And then we also experiment something more, some more application to see what's happening, I guess, in the most famous examples of the most classical studied varieties, congruence varieties. And so it was natural also to consider M3. And so what about M3? Of course, we don't have to select a specific congruence. Or yes, actually, we have to select one, but the only non-trivial choices are the 3 atoms that are equivalent. So you can pick which atom you prefer. In this case, I will use gamma. And so the first thing that you can easily prove is that alpha 0 and beta 1 and beta 0 and alpha 1 are comparable. And if they are equal, then the limit is actually the 0 congruence. Furthermore, in this case, at the beginning, we had to add some hypotheses on the M3 that we consider. this was because, of course, if you had, so the hypothesis that we had is it was about the pairwise permuting congruences. So we suppose that our copy of the M3 that we consider in our algebra has pairwise permuting congruences. This was to simplify the otherwise really hard construction that you, really huge construction that you can get in this case. If you assume the permutability of the congruences of this sublattice, a lot of the congruences are collapsing. This is an example of a lemma that you can obtain. And in this case, you can be able to characterize what you produce given the considered congruence. So the theorem that you obtain characterize A of gamma. In the case of you start with an M3 consisting of pairwise permuting congruence. And in particular, if you consider the congruence lattice of A of gamma, you consider its sublattice generated by the congruence in display. So you take eta 0, you take alpha 0 with gamma 1, alpha 0 with beta 1, alpha 0 beta 0, gamma 0, and beta 0. Then you can prove that is isomorphic to M33. That is the resulting display. So that actually this lattice is admissible in the congruence variety of a variety that admits an M33 with a pairwise permuting congruence can be also derived by a result of freeze that actually prove that in the case that you have a variety that is not semi-distributive, so that is admitting M3 and there's a weak difference term that is implying that actually your M3 has permuting pairwise permuting congruences, then you can get a larger class of lattices, largest class that is including also M3. But we could also prove something more, that in general, that given a variety, if you have an M3 in your congruence variety with pairwise permuting congruence, then you also include so basically two chains of lattices, Rn and Sn. They are called rod and snakes, and are the families in display now. So the snakes are these in the left, where you have copies of M3 attached from yes, either the top right edge or the top left edge. The rods instead are the one that you can build simply attaching by the top right. You can also include some bigger actually families, the so-called generalized for rods and snakes. So where you select how to attach the either on the left or either on the right, and you form so a lattice in this way, forming some kind of path or path of M3s, and also some other lattices. The strategy to prove that actually you include also you can produce these lattices in this case is not using only the second power, so it's not only considering A of gamma. With A of gamma, you start with the first one, attaching the first one, and then to attach further copies of M3, you have to consider a bigger power of the original algebra. So in general, you have to consider this case, I guess, eta 0, if I remember right. So instead of a congruence of the original algebra as the base set, you have to consider a congruence of the congruence algebra that you were considering, and so on. So you are exponentially increasing the power of the algebra that you are considering, where n is the number of the n of the power is the number of m3s that you want to attach, and then you can prove, of course, this result that I stated before. To put it in another perspective, let me also introduce the class of the omission class of gamma, when gamma is a class of lattices, is simply the the class of varieties that omit L as the congruence lattice, as a sublattice of the congruence lattice of an algebra in the variety. So mainly are those varieties that, where L cannot be a sublattice of the congruence lattice of your algebras. And also using a remark, or I would say something proved by Keith, that mainly stated that if you find an M3 with pairwise permuting congruences in your variety, in the congruence, in the congruence lattice of an algebra in your variety, you can find another copy of it. Sorry, let me reformulate this. So if you have a copy of M3 as a sublattice of a congruence lattice of an algebra in your variety, you can find another algebra such that it has an M3 in the as a sublattice of the congruence lattice, and this M3 has pairwise permuting congruence. So mainly you can get rid of the pairwise hypothesis for the admission of Rn and Sn, and also of M33. And so, yes, and so you obtain basically that the filter of omission of M3, that is the variety of the class of varieties of congruence semi-distributive variety, can be actually obtained also by the union of the filters of omissions of either the roads or the snakes. To conclude, I want also to mention some results that are actually not published. So far, all these results are published. Of course, the next question maybe could be to consider D2 and to study what you can get using the technique that I mentioned before, applied to D2. Of course, in this case, there are more congruence involved. There are also basically, this is the problem. If you want to also to reduce a bit the complexity of characterizing the structure that you can get, it's better to start with one of the bottom non-trivial congruences, so one of the atoms, since then the copies given by the homomorphism theorems and the things that actually are collapsing over one of the two atoms are more congruences. So you simplify the lattice basically that you get. And to characterize those cases, you need to consider some chain of congruences, mainly these chains. Basically, you take gamma and beta that forms kind of a pair, like in the M5, even if it's not sublattice in this case. But the idea is like they work as the beta and the alpha and the gamma in the M5, basically. And so you create this kind of congruence generated by the gamma I circle, this kind of congruence term that you obtain, that was the one that we were considering to split the two cases. Was this one? Yes. This is actually done to characterize what you obtain in the interval that is creating problem join wise. Let's say this is the idea, even if it's rough. And then you obtain this characterization. So if you have D2 as a sublattice in the congruence lattice, you consider A of me, and you apply the construction that we have seen before. You consider these gamma i's congruences. Then you have these three cases. Either you obtain this kn-1 that I will show you in the display. Either you obtain a kn-1 star, that is another one, or k infinite. This depends how the chain of congruence gamma I is behaving. If it's stabilizing, then you have the k star or the k and 1, so a finite lattice. Otherwise, not. Those are the two lattices, quite complicated. With some effort, maybe you can still see the copy of the 2 over the 2 factor congruences eta 0 and eta 1. So both are finite, and basically you find some copies of the square that we have seen in the M1 example, and so how many copies? It depends on how many congruences you are forming the chain gamma I. And this chain of squares is ending with a square when we have the start, ending without a square, so with the collapsing case when we have the first case. When the chain is infinite, then you get what I call the K infinite. It was also used for another lattice in the literature, but still the notation is a work in progress. That is this lattice where you have an infinite chain of these squares. You can also, with the same strategy, characterize still the case of N5, but when you don't restrict to an interval when you have only two congruences, and you obtain similar lattices, basically as before, but where the copies over the two kernels of the congruences in this case are, of course, not copied of D2, but copied of N5. So that's all, I guess, what I wanted to say. Those results are appeared in the first paper that is published in the Journal of Algebra and Computation, and in a manuscript, the last part, the last complicated part that I have, I'm still working on it. And I guess that's all, and thank you for the attention.
Thank you.
Okay, thank you.